So we will pass to the next speaker, Sakya.
Well, it gives me a great pleasure to introduce our fourth invited speaker, a good friend, a colleague, and I should say also a continent fellow. Both Sossina and I were born part of Africa. So Professor Sossina Haile, she's professor of material science and chemical engineering at Northwestern University in the United States of America.
Her talk will be about the state of the art in solid acid fuel cells. And thank you very much, Sossina, for being here with us.
Okay, thank you very much. My pleasure. Also to be following such great speakers. I've had the opportunity to learn a lot, so thank you to those who've already spoken. Okay, let's see if I get this going. So I will be talking about kind of an unusual class of fuel cells, one that I think most of you will not have heard of before. So I will introduce it, but I'm also going to put this back in the context of the global energy picture. And so just to think about where fuel cells could be in a sustainable society, an energy sustainable society, you could imagine our carbon-free energy sources up here delivering energy that we can then convert in some way using the wonderful hybrid perovskite solar cells, for example, and storing that energy in the form of batteries. So once we capture electricity out of that, and maybe deliver that through an existing infrastructure for energy electricity delivery. We could also think about converting that into some sort of fuel, and it could be hydrogen, for example, and then deliver it through some infrastructure. Of course, hydrogen is challenging, and you know, the need to create an infrastructure for that has in some way really held back hydrogen fuel cells from making their way much more visibly into an energy infrastructure. But if we could do that, the nice thing is that we could then have a fuel cell that converts that hydrogen directly into electricity and gives us water as a product. Now, if we think about, well, that's a little bit hard because of that infrastructure challenge. So if we'd still like to take advantage of that fuel cell, you might think of creating carbon-containing fuel. And in that case, you would need to take the CO2 that you generate and think about an infrastructure to turn it back and bring it to this plant, whatever, could be a solar plant or biomass, sort of, you know, capturing CO2 from the atmosphere using actual plants to then be able to create the fuel. In either case, we have the fuel cell here that is taking our chemical fuel and giving us electricity in the highest efficiency way possible. So regardless of what the nature of the fuel is, as long as the fuel cell is able to work with it, it has the advantage of that high efficiency, and ideally it produces no other products besides the water and the CO2. Okay, so that's where our fuel cell fits in. And then briefly how a fuel cell works. If we have an example here where we have an electrolyte, that's a proton conductor. And if we bring hydrogen and oxygen on either side, the two really want to get together, lower their Gibbs energy, and that would be the reaction overall. In order to do so, as we bring the hydrogen, that would need to drop off its electrons and turn into protons because we have this electrolyte here that only allows the protons through it. We need some sort of catalyst to break that up. It's actually, this catalytic reaction is generally easy. So even though it you know, still requires a catalyst, that's not a large overpotential. The protons go through the electrolyte. The electrons then here power our external device. And then on this air electrode side, the oxygen will react with the protons, pick up those electrons that have come through the exterior circuit, and then give us our water. So that's the overall scheme here. Our reaction, again, driven by the idea that we're going to be lowering the Gibbs energy of our reactants compared to our product here, and we need to catalyze these two reactions, these two half reactions. So we have a catalyst also at the air electrode, as we did at the fuel electrode, again, delivering our water as a product. So we have in fuel cell mode, we call this the anode, and at the air electrode is the cathode. And the idea is that a fuel cell combines the clean, efficient operation of batteries, but it is refueled like an engine, so you don't have a large recharging time. But of course, batteries are getting much better now in terms of the fast recharge. The way that we measure fuel cell performance is to look at the voltage as a function of the current that's being drawn from it, and we convert that to current density so that we have a metric that is realistic in terms of comparing device performance. Our open circuit voltage is determined by the Nernst, sort of the Gibbs energy of this overall reaction. We just divide that by the number of electrons and Faraday's constant to get the open circuit potential here, or open circuit voltage. And that's typically around a little bit over 1 volt for a typical fuel cell. And then we, as we start to draw current, we see the consequence of various loss mechanisms. First of all, we may even have a little bit of a leak or crossover such that we don't actually get the ideal open circuit voltage. And as we start to draw current out of our system, initially we see a decrease because of slow reaction kinetics. These are what are called the overpotentials at the 2 electrodes. Then we start to see the impact of the resistance of the electrolyte itself, so kind of a linear regime that shows up, which is our ohmic losses. And then if we go to very high current densities, we're really not able to deliver the gases into our fuel cell as quickly as we're trying to extract power out of it or extract current out of it, and we start to see what are called mass transfer resistance losses. So this is the voltage. We're interested, of course, in the power, and the power is just the voltage multiplied by the current. So the power density is voltage times the current density, and it gives us a curve that looks something as shown here. Typically, we operate at around 0.7 volts, which gives us a good balance of efficiency. So the higher the voltage, the better the efficiency, and a reasonable power density. Of course, you could have very high efficiency if you're not actually using much of your fuel, if you're up here. And if you're operating at very high power, your efficiency will be low. Okay, so there are lots of different types of fuel cells, and they're generally differentiated by the nature of the electrolyte. So there's the polymer exchange membrane, alkali fuel cell, phosphoric acid fuel cell, molten carbonate fuel cell, and solid oxide fuel cell. And you can see that I've ranked them here in terms of the temperature at which they operate. And the temperature is really set by the nature of the electrolyte because those ions need that thermal energy to get across the electrolyte. And in general, the idea is that if you go to lower temperature, you have the benefit of easy thermal cycling. And if you go to high temperature, your catalysis is faster, just that thermal excitation over the energy barriers. So you get better efficiency. It also means that you have better fuel flexibility because other fuels besides hydrogen would be able to be catalyzed to be oxidized. So you might think, well, what if I want both of these? What if I want easy thermal cycling and I want good flexibility in my choice of fuels? Well, you can just switch the direction of the arrows and hope that at some intermediate condition, you will actually combine the benefits of fuel flexibility and efficiency with easy thermal cycling. Now, if you look at your options here at this intermediate temperature regime, the challenge is that these are corrosive liquids, phosphoric acid and molten carbonate. These are all challenging to work with. And so there is this target regime of developing solid electrolytes, solid ionic conductors that operate in this intermediate temperature regime. And there are some, and in my laboratory, we work with all 3 of these materials that sort of skate at the top of the conductivity in these different temperature regimes. And what I'm going to tell you about is what we've done with this particular material, cesium dihydrogen phosphate, which is a proton conductor. And the nature of this material is such that we have here these phosphate groups, cesium ions that form in a monoclinic structure here at low temperature, something that looks close to a cubic structure. And with just a little bit of heating to a high temperature phase where we have a transition, that material transforms to this cubic phase. It's a cesium chloride structure type. And the phosphate group, which was sitting here in a specific orientation, undergoes a rapid reorientation. It's a tetrahedral unit that's sitting in an octahedral site of octahedral symmetry. And so it's got 6 different orientations. And as it reorients here, it moves the proton from one oxygen to the next. And every once in a while, the proton can transfer to the next phosphate group in the neighboring unit cell. So we have this dramatic increase in conductivity as we go through the transition from the ordered monoclinic to the disordered cubic phase, yet it is still solid, crystalline. You take a diffraction pattern of this, and it's a very sharply crystalline material, and it has this very high conductivity. So using it as a fuel cell electrolyte, it has some advantages and, of course, some disadvantages. One is that it's a pure proton conductor. So Zakia mentioned that I'm originally from Ethiopia, so sometimes I like to say that our electrolyte conducts the protons where in the sense that they don't need a water molecule to transport them in the way that the polymer systems do. So our protons are marathon runners. They don't need a limousine to get them across the electrolyte. The other advantage that there's no electron transport. This is a very large band gap material. And because we can make it as a true solid, it's impermeable to fuels like alcohols that you might want to consider if hydrogen is a challenge. The magnitude of the conductivity is independent of the humidity, which is nice. The material is generally stable to about 280 C. It's inexpensive. Cesium is dissolved in the oceans in very large quantities. The electrolyte is also chemically non-aggressive with respect to catalyst platinum in particular. So again, if you compare that to the polymer systems, the polymer tends to dissolve and reprecipitate the platinum, so it coarsens. But there are some drawbacks, as I said. The material is water soluble, so we have to operate at above 100 C. There's also a challenge of dehydration. So we have to maintain a sufficiently high water partial pressure that we don't have this reaction occurring. And I would say that perhaps the biggest drawback is that for the community, it's hard to think of salt as an engineering material. So this really does have the properties of salt, your table salt. So it's very unfamiliar processing, and it has poor mechanical properties. And there is a volume change at the transition, which I'll show you, we thought would be a drawback, but it actually isn't. So we can make fuel cells out of this. This isn't exactly to scale. So this is about a 50 micron electrolyte. So I've shrunken that so that we can see the cathode and the anode in it as well. The cathode has the electrolyte material here with platinum covering it to make a good electronic contact and also good proton contact. And then it's porous so that the oxygen can make its way in. At the anode side, we have a composite as well, which is the platinum on carbon. We bring in, this is commercial material, and then we mix that in also with the electrolyte, so we have good proton conductivity. So we have relatively low platinum loading on the anode side, but quite a high platinum loading on the cathode side. This is our typical fuel cell performance. So it's always interesting to me to see solar cells and their very small amps per centimeter squared. This is actually quite low for a fuel cell. We've able to get higher power densities if we make this electrolyte thinner, but we've really focused on trying to improve the electrodes before taking that step, which is a little more direct, whereas improving the electrodes is certainly the scientific challenge. So that works well. Our anode works extremely well. Our cathode has some degradation challenges, although it is usable as is. The anode, I'll talk about sort of the benefits of this anode and why we can, how we leverage its behavior. So, we went through the effort of making a small startup company. So my first two PhD students made a company, Superprotonic. Tom Friedman, who is a columnist for the New York Times, visited our lab. So we set it up with a cell phone powering the fuel cell, a fuel cell powering the cell phone there. 2008, there was an economic crash. So the company went under and started over a SAFC cell. And now we've demonstrated direct methanol fuel cells that actually operate in the oil field. The idea is that we're replacing the methane use in the old fields, which releases methane with methanol use, and then that conversion means that you have water and CO2 being released, which is much better than methane release. But of course, there's an economic crash now in this market, so this is a challenging time for this company in particular. But I will show you some of the other things that have been done at the startup, is that we can make these stacks. And this is what you do to increase the voltage of the fuel cell, is that you make multiple layers. So once you pile them up in series with one another, then you get the high voltage. And so we can go up to 1.4 kilowatt system, and it all scales really very nicely. The other thing is that I mentioned that there's this phase transition. So despite this phase transition, we can cycle the temperature through the transition and recover the power density. So this is the peak power density, which is that top point in the power curve that I showed you, is quite stable over several hundred hours. This is only up to 150, but it continues. And the voltage is also quite stable. So everything looks great. At thousands of hours, we start to see some degradation in the cathode. But again, I'll tell you about some of the benefits of the anode system. So one of them is that we have great carbon monoxide tolerance. Now, if you're getting your hydrogen from electrolysis, it doesn't matter. But we still typically in the world today get our hydrogen from methane steam reforming. And so it has a little bit of CO in it. And so what we can do is input some CO in with our fuel that we're testing this device with. And what you can see is that there's really very little impact on this polarization curve as we increase the amount of CO. And so the electrode resistance that we measure for this electrode, and again, I won't go through the details of how this measurement is done, but the key is that the resistance is stable with quite a high CO input in this region here. And it's only when we have very high amounts of CO that we start to get some electrochemical resistance at that interface. And so in fact, the CO is being consumed by water gas shift reaction because we have a lot of water that's also coming in, and that is increasing the hydrogen that's available to the anode, and the CO is being converted to CO2. So that's great. And this is also what drove us to consider these direct alcohol fuel cells. In this case, we have the our electrolyte with our this is and we've got the electrocatalyst on either side, but on the fuel side we introduce an additional what's called a reforming layer. So this is a common catalyst for converting methanol into CO2 and hydrogen, and that hydrogen then becomes available for our fuel cell. And what's nice about this entire system is that the fuel cell is exothermic because we have these resistance losses, whereas this reforming reaction is endothermic. So we can match these such that the thermal balance is good, and then we don't have to insulate quite so significantly to manage the thermal management of the system overall. So how it performs then is when we have hydrogen here as our fuel, and compare that to delivering methanol with a lot of water as well. So 42 volume percent methanol and then balanced steam, because we need that to do that reforming reaction. We can see that we're getting about 85% peak power compared to hydrogen, which is a really good value for polymer systems. You might be on the order of around 10%. And to prove to ourselves that the reformer was actually doing the work, we compare the performance of the cell without the reformers. So we've got no reformer. We're comparing hydrogen to methanol, and you can see there's a big drop. And the other thing is that we then just delivered perfect reformate, which has 1% CO, 24% CO2, and then balanced hydrogen. And of course, we humidify as well. And we can see that if our reformer were better, if we're a little bit better chemical engineers in this sense, we could get even closer in terms of the power output from our direct alcohol fuel cell. And so basically, we're just getting a little bit of dilution effect here. So that works really very well. That's great. And we said, well, how about ethanol? Because maybe you're, sitting on the plane, you've run out of power, and what kind of fuel can you get? You can't actually get methanol, but you could get a little bit of ethanol. And that is also pretty good, not as good as the methanol, because ethanol is harder to break the CC bonds. And we said, well, let's compare that with the thing that you might actually get on the plane, which would be 80 proof vodka. And that works just about as well as our clean ethanol. So I like to say that's more demonstration of the impurity tolerance of our anode. So if we go back to the idea that our hydrogen fuel cells are challenged by a lack of hydrogen delivery infrastructure. So I described to you how we can operate on the direct methanol fuel cell. But another possibility is to think about ammonia as a hydrogen delivery vehicle. So you could do on-site conversion to hydrogen, or you could use the ammonia in your fuel cell. The reason that you'd like to do on-site conversion to hydrogen is that you don't really want consumer pumping ammonia into their vehicle, for example. So if you could do on-site conversion to hydrogen, that would be great. And you would need to have something that could convert the ammonia to hydrogen on small scale with very high efficiency. So this is actually something that ARPA-E has been promoting as an idea, that you could use your excess wind and solar that are delivering power maybe when you're not using them, use that to generate ammonia. So I'm not going to talk about this step, but then if you had that ammonia, you could deliver it through pipes in a way that's much easier to do than hydrogen, and then do the on-site conversion to hydrogen. And that would require a little bit of local electricity here, but the idea is to minimize the energy requirement to do that. And so we went ahead and explored the possibility of using our cells for this approach in terms of this particular step, which is where you use a little bit of electricity and use that to power the conversion of the ammonia to hydrogen. And the advantage here also is that you can do electrochemical pumping so that you can create high pressure hydrogen that you would be putting into a tank, again, to put it into a hydrogen fuel cell vehicle. And so we're doing a design here then that's very similar to what I showed you for our direct methanol fuel cells, which is to combine some sort of chemical catalyst with our electrocatalyst layer. And this also gets around what I told you was our cathode is kind of lousy. In this case, it would be, we don't need it here because what we'll be doing is evolving hydrogen because we're not doing the fuel cell step, we're doing the ammonia to hydrogen conversion step. And just to show you a little bit now, a little bit of chemistry of what we do. So we're using a ruthenium-based catalyst, depositing that on some multi-mole carbon nanotubes, but we also do this on cheaper Vulcan carbon. We prepare that electrocatalyst. This is the chemical catalyst material, and it's, get some small crystallites here. We have a relatively high ruthenium loading, but ruthenium is fortunately not quite as expensive as platinum. And then we promote it with cesium. This is not our recipe. There's quite a community doing this thermal conversion of ammonia to hydrogen. So we borrowed the recipe from that literature. We put the cesium nitrate on it. And so we get this cesium nitrate promoted ruthenium on carbon nanotubes. Okay, great. And so let me show you what we then do. So now we have this two-layer electrode. Once again, we have our an intermediate layer here of that electrocatalyst, which is platinum on carbon. That's a commercially obtained material. And then we have the that's mixed in with our electrolyte to provide the proton transport. And then we have our proton conducting electrolyte layer. And here we have that very easy to make platinum counter electrode, which has that relatively low platinum loading. And what we can see is that if we deliver ammonia to our cell, we get current density out of it. And we want to show you that that's exactly equivalent to the hydrogen that's being produced. So if we have 100% Faradaic efficiency, that means that every single electron that goes across, through our exterior circuit is balanced by a proton that's going through our electrolyte. And so we can compute then the hydrogen production. And so we did a quick test to make sure that our cells operate with hydrogen. So this is, we get an open circuit voltage here that matches what you expect based on this Nernst equation. So that means we have 100% dense electrolyte because we get the right voltage. And then as we drive the hydrogen through, sort of we are unable to get more current once we're at around 90% of the maximum. That tells us that we're not splitting any of the water that happens, that we're supplying here. We wouldn't expect it to at a relatively small voltage. Splitting water is a holy grail, of course. And if we were doing it at such a low voltage, that would be great, but we're not. We're just, in this case, breaking up the hydrogen and pumping it out on the other side. When we now introduce the ammonia, you can see this is how much current we're getting out of here. And when we have more ammonia, we get more current, as you would expect. We go back to the lower ammonia concentration, and we can see that we are almost about the same performance level, so we have reasonable stability. And this is now to show you that we indeed have 100% Faradaic efficiency. We put a mass spec on this side. We have to have a condenser here, and then we detect what's coming out on this side. So what we see is when we detect the hydrogen that's produced, compare that to what we expected from the flow rate, that's exactly at 100% efficiency. We have no, we wouldn't be able to tell if ammonia is coming across because we have this condenser, but we look at the water and see that the pH hasn't changed. So we know we're not leaking ammonia across it. And we also check the gases on this side and show that there was no nitrous oxides being produced. And if we compare that to what's happening in the literature, the amount of hydrogen that we produce per catalyst, gram of catalyst material, we have a much higher production at this relatively low temperature compared to all these other results in the literature. And again, we have a cracking catalyst, a hydrogen oxidation catalyst, our proton conducting electrolyte, hydrogen evolution catalyst. We can pump up the hydrogen here. The pressure is required. And the gram of catalyst that we're calculating is all of the catalysts in all of these layers. So all of the platinum as well as the ruthenium. Okay, so then to summarize, these solid acid fuel cells offer lots of advantages and purity tolerance. I didn't show you the sulfur tolerance, but it's also quite good. You can see that we can pass ammonia to that platinum, it doesn't mind. And if we have ruthenium, we're actually able to convert that to hydrogen. So we have good fuel flexibility and ideal temperature for thermal management. And I didn't describe to you our real challenge that we're working on is dealing with the cathode to air electrode. There's some potential for commercialization that's going on. And again, as I said, we have this great way to produce hydrogen from ammonia. So with that, let me thank all the folks who have done the work here over the years, current students and postdocs working on it, working away. And again, of course, we all appreciate that it's all our students who do the work. We are just the people who get to be the cheerleaders and share it with you, and also thank the funding for supporting this work. And thank you for your attention.
Sossina, thank you very much for a very interesting talk. We have one question if you go to the Q&A section.
Okay. Right, so that was how we measuring the amount of hydrogen. That was through the mass spec that we showed you there. Yeah, and one thing that I didn't comment on is that when we operate the ammonia cell, we are supplying a high amount of hydrogen on the side that we're producing the hydrogen. That's to be able to prove that we can be able to pump up beyond the hydrogen that's already there. That's also just sort of the way that the community does it. when we did the Faradaic efficiency measurement, because there's such a high background of hydrogen, we didn't provide any hydrogen on that side at all, and then just detected the hydrogen that was emerging at the mass spec. And let me just also emphasize, that means that you do get pure hydrogen out of it. There's nothing else that can come across that electrolyte. Yeah.
Okay, is there any other question? Sakia, please.
Thank you, Sossina. This was a very nice talk as well. And I learned a lot because it's not my field, but I have a couple of questions. Did I understand you right when you say you would like to convert liquid ammonia to hydrogen? It's liquid ammonia?
Well, the delivery infrastructure can handle liquid ammonia. So when we're doing our experiment, we're doing it at 250 Celsius. So it's in vapor phase.
So it's minus like 28 Fahrenheit or something, very cold, right?
Yeah, and again, there is already a pipeline for ammonia delivery. And so you pressurize it a little bit. That's the other way to get around it. I'm not any sort of specialist on ammonia delivery, but there is an existent.
So it's commercially feasible, right?
Yeah, and it is done. I mean, so ammonia, of course, is used in fertilizer. So there's a lot of pipeline that's already done. There's also delivery in trucks that's already done, and some trains as well, although that's decreasing compared to truck delivery. But yeah, it's all exists.
Thank you. The other question I have, when you say dilute hydrogen, how dilute is it, and what do you mean by that? Do you have? Yeah,
the reason that we did that experiment, it's not critical at all. So we did something like 2% hydrogen. So the reason we did that is that you can have a high hydrogen concentration on one side, a low hydrogen on the other, then you get a concentration cell, that's called, and then you can calculate the voltage that you expect across it. And then when you get that voltage, you convince yourself of two things. One is that there's no leakage of hydrogen across the electrolyte, and the other is that there's no electronic leakage either. So that proves to us, although we knew it because the band gap is so large, that there's no electronic leakage.
Okay, and would you comment on the composition of your anode? If I recall, was it platinum at what, graphite or something like that?
Yeah, it's platinum on what's called Vulcan carbon. This is commercial standard used in polymer fuel cells. And it's 20% weight platinum on the carbon support. It's usually around 2 to 3 nanometer particle size. And then you mix that in with the ionic conductor to be able to now transport both electrons and ions. Yeah. And unfortunately, we can't use it on the air electrode because the carbon will burn up.
Thank you very much. Very nice talk again. Thank you.
Just one very general question about these electrodes that Saki asked for. The amount of platinum seems to be very low, but I guess everybody questions is a possibility for using such amount of platinum for the commercial applications in the future.
Yeah, so I mean, I appreciate that you said our platinum loading is low. It's actually, we're pretty high compared to the polymer systems. And that's on the air electrode side. And the reason that we have a high platinum loading is because, as I said, we can't use carbon. So we're using the platinum to be the current collector, which is a horrible use of platinum because the oxides are not really very conductive at these temperatures. So we are kind of been stuck there. Now, I think, we've been thinking more and more about solutions. So let's imagine that we could get to a reasonable platinum loading. What does a reasonable platinum loading mean? So from the car company perspective, they're looking at, can we get to something like comparable to a catalytic converter? And in that case, we don't think about that as being a limiting step for, being able to manufacture automotive fuel cells. I will say that at one point in time, I tried to extrapolate how much platinum would be needed given what was at the time sort of DOE targets for platinum loading. And it was kind of dire. I'll be honest with you about that. And we would have to start thinking about platinum recycling, because from catalytic converters, it actually ends up in sort of an exhaust from the cars and ends up in the soil, which is also, it's inherently a problem. But so from my perspective, I'm still hopeful that at 250 C, we might not actually need platinum. So we're still working on that, but it's been hard going.
Very nice. Thank you very much. If there's no questions, we thank you very much for being here with us, Sossina. And we will invite the next speakers.